Thank you, Barry, for your kind words for the introduction. Ladies and gentlemen, good morning. The title of my talk is a DC power solution for AI data center and the future perspective. I think all the journeys coming from the demand needs. Okay, this is my outline. As we can see, due to AI data center, the demands of the power increased dramatically. So the revolutionary change has been built up from the power layer all the way to the server rack and to the chips. So we'll first introduce you the DC-DC power module solutions, not only for the high efficiency, but now the high density is more important. And follow that, I will introduce you the advanced package and solution to realize how the high density power module. And finally, I'll give the future perspective. So let's take the NVIDIA GPU as an example to see how the demand is. A decade ago, you can see their GPU K40 start from 28 nanometer all the way to the Blackwell 4 nanometer. So the process from the transition number from 7 billion to the more than 100 billion. And the die size already reached the roof. That's roughly 100 millimeters square, which means a radical size. And then you can see the power increased dramatically. Now it's, for each one, will go over to 1 kilowatts. So this is dramatically power needs from the AI. So as you can see the photo here, the GB200, actually there are two dies, seamless joined together. They have the underneath interconnects using the CoWoS interposers. So in order to enhance the calculation power computing capability and also reduce the power. And furthermore, if you look at the Rubin Ultra, which will be released, probably a couple of years later, they will have four GPUs in series. So it means that more and more power needs the efficiency and within a very small area. So we need a very high power density. So in this regard, we have the revolutionary change for all the power, particularly the DC powers. Okay, as you can see now, the GB200, the rack. Okay, each one have 72 GPU, consume 140 kilowatts. Each air conditioning consumes less than 1 kilowatt. So you can see how many air conditioning operating for just one rack. So this is only now. For the next year, start from the Rubin, the GPU number will go up to 144 and consume more than 400 kilowatts. And eventually, a couple of years later, the Rubin Ultra, you can see they have 576 GPUs. And also the server is no longer horizontal, slightly become the vertical. So in order to have higher density of the GPU, so in this case, you will consume 1 megawatts. So if the hyperscale data center have 500 racks, you will consume more than 500 or 600 megawatts. It's almost equivalent one nuclear reactors, the total output powers. So the demands increase dramatically because the demand increase because of the computing power needs and the electrical power will correspondingly to increase. Not only the active device and also the passive component also be asked to increase the power density. And we are the specialized in the magnetic inductor makers. As you can see, we have been asked from the customer not only also increase the power handling capability to one single coil to dual coils and to quadruple coils. So everything, concentrate, focus on the power density. So in this regard, so the power rail from the power plant all the way to the rack. This is the existing power systems. We have the AC powers from the rail, and you have the UPS, and all the way the AC power to the rack. So we have the AC to DC and the DC to DC. Finally, we have the voltage regulator to the final stage. But this no longer cannot be satisfied the power needs from the chips. So everything has been changed because your AC-DC power cannot provide enough power to the chip. So we have to change it to modify the power rack. This is the next generation, the high voltage DC architectures. So from the power plant, we have the solid-state transformer from the AC direct to the DC, for example, like the 400 volts. And this is the solid-state transformer, probably needs silicon carbide, need a couple thousand volts breakdown voltage, and the DC power all the way to the rack. So inside the DC rack, only have the DC-DC conversions. So everything from the 400 volt to 48 volts, and all the way IBC plus the final voltage regulator to like the 0.75 volt to the chips. So because of the higher voltage, so we can reduce the current in this case, so the power efficiency can also be increased. So you can see the architectural wise has been changed from the current power rail to the rack. So it's more Delta and also the Cyntec. We have been realized for this DC-DC converter all the way from 400 volt to 0.75 volts. So it becomes all the modularized. The reason why we become them all the modularized because the modularized can provide higher power density within a very limited space. So at the first stage, we have 400 volts down to the 48, and then you have the IBC conversion, either 4 to 1 or 8 to 1, and the final stage will be 12 to 0.75 or the 6 volts. It depends on your designs. So, for the semiconductors, we also have seen some changes. For example, in the first stage, 400 volts, gallium nitride and the silicon carbide play an important role here from the primary side, and also from the secondary side. For example, you need a 100 volt GaN devices for the secondary sides. And also for the IBC, these 48 volts, we have used a lot of the GaN devices inside here. And the final stage currently is still predominated by the silicon semiconductor, but from my perspective, like the low voltage GaN will play a major role in the near future. I will talk to you later. So again, because we need a higher power density, we need a modularized, and also because of the high voltage DC, the GaN and the silicon carbide become more important. Here I highlight the GaN performance versus the silicon superjunction MOSFET. Because the wide-bandgap device, the advantage is operate high voltage. So the breakdown voltage, operation voltage 650 volts. You can see, compared with the silicon superjunction, there is 10 times in terms of 10 times better in terms of the RDS zone, which relate to conduction loss, and the QG, which relate to the switching loss. So the 650 volts, they have 10 times compared with the silicon superjunction. But we down the voltage down to 100 volt, this benefit becomes 3 times, and down to 40 volt becomes 30%. But even 30%, or down to the 15 volts, the gap between the compound semiconductor, gallium nitride, and the silicon become narrow. But there is another advantage for the GaN device. I will talk to you later. Here, I show you we have realized the product in Delta that for the 400 volt convert into the 48 volts and with 3 kilowatts. And you can see the performance over 98.5% the peak conversion efficiency. And the power density can reach 2.4 kilowatt per inch cubic. Okay, so this is we already established this for the for the server. If the one unit they needed 10 kilowatts, we just in parallel 3 or 4 modules. So you occupy a very small amount of the space. If compared to AC to DC, if you want to handle 10 kilowatts, your power module will become significantly large. There's no way you can put into the server. So the modularize, along with the high voltage DC, is a future trend, and actually it's coming in the corner. So here I show you we are already in the mass production, the 48 to 12 volt, we call the IBC power modules. And we use 4 games, each as a 100 volt breakdown voltage in this small size can handle the 1 kilowatt powers. This is another one we already in mass production. Actually, we deliver millions pieces last years. So, you know, all the passive components like the magnetic choke and also the transformer were embedded inside the PCB. So it can reach very small profiles in this case. And the low profile, I mean the height of the module become very important. And I will show you later. This is another one with the same footprint. We upgrade from the 1 kilowatt to 1.5 kilowatt. Can maintain the efficiency roughly 97.8%. So as you can see, now the power density is very critical. Now already have few customers use our 1.5 kilowatt power modules. For the last stage, we start from the 5 years ago. That's the 12 to 0.75. And we have the driver modes on the buttons, and later we put the driver modes on the top. And then we have low profile, 4 millimeter high. And also finally, we have TOVR choke in order to improve the transient performance. So altogether, that's the package become very important. How to make it smaller and embedded and everything low profile, you know, is essential for the next generation power module in the AI data center. So this, let me talk about the future perspective. I borrowed this slide from the EPCs. As you can see here, their performance-wise, from the right-hand side, for the 40 volt breakdowns, they have the 70% improvement compared with the silicon device. And even though the gap becomes smaller, like in the 15 volts, but they can achieve like 2 milliohm per millimeter square, which is better than the silicon split gate MOSFET, for example. But this is for the DC RDS on. But if you consider, later I will tell you, there's another important factor for the GaN devices. This slide I borrowed from the Fast Silicon Carbide, which is a new startup in Taiwan. They show me that with the same package size, silicon carbide device will be able to perform better RDS on as compared with the silicon and the gallium nitride. So in terms of the conduction loss at 600 volts, silicon nitride has a better performance. For the switching loss, of course, GaN is better. So, so this is not only the GaN, but also the silicon carbide. And lastly, I would like to show you the needs from the core, power core. So 5 years ago, our modules has been put in the AMD MI250. So it's we call the later power delivery, but at that time, power level is not so high. But eventually, the power demanding increase. So the length between the lateral diffusion and lateral delivery, power delivery, becomes too long and consume power loss. You know, 3 years ago, Tesla Dojo proposed the vertical power delivery, which means the DC power directly from the backside of the silicon chips. Unfortunately, Dojo has been terminated, but the vertical power delivery become important and is very popular now. And even for TSMC, they propose the last conversion, they call the integrated voltage regulators, is inside interposers. So it tells you that the last DC power conversion should go closer and closer to the chips, which means you have very limited space. And also it translates that you have to operate at a very high frequency. So I download the Infineon the website. You can see the last stage, Infineon already have the very good performance with the dual phase with the 1 amp per millimeter square all the way to quadruple phase, 2 amp per millimeter square for the last conversions. And then we just finished our prototype with the same footprint and 5 meter high, 6 voltage in, and we will be able to reach 2.8 amp per millimeter square. This is a quadruple phase, the modules. So our modules, we collaborate with IC vendors. There are 4 phases, and also we homemade 4 magnetic inductors, and also we embedded the capacitor, output capacitor inside the PCBs. So you can see very similar to the Asian temple in the Greek, So it's very tough challenges to build up this kind of high density power modules. And it's not only the engineer job, but also it's kind of the art. But the story haven't finished yet. We are asked for the next. What is the next? Next is the high. Current our high is 2.5 millimeter high. We were asked to become the 2.5 millimeter height. And the frequency, currently we have 1 megahertz, have to go up to 5 megahertz. And the current density go up to 6 amp per millimeter square. So it's very, very challenging. And the customer needs, because more and more limited space, we need a higher density. So we don't know, we are still developing this technology for the next generation, but it's very challenging, particularly the package. So I didn't draw this cartoon. Instead I asked the ChatGPT to do it because this is a semiconductor forum. So here, the voltage, for example, we convert from the DC voltage for 600 volt or even 800 volt down all the way down to 0.75 volts. And the silicon carbide, as I show you, can operate not only the few 1,000 volts, can all the way down to the 200 volts. So you start to take some territory of the gallium nitride. And the gallium nitride, more importantly, they will be able to go down not only the 40 volts, all the way to 15 volts. So if you consider the 400 volt all the way to 0.75 volts, the voltage reduction is almost 500 times. It means the current increase 500 times. So it translates your wafer consumption become 500 times. Okay, that's a huge market. Okay, so from my point of view, the gallium nitride you will see a very explosive growth in the near futures, because not only for the current density, but more importantly, because the last conversion will have very limited space, have to operate over 10 megahertz. The only gallium nitride can do it. Because for the silicon, if you look at the basic semiconductor, if you want to have the very high switching frequency, somehow you have to trade off with your current driving capability. Okay, this is a compromise, but this trade-off didn't happen in gallium nitride. This is basic fundamental physics. So gallium nitride is the only candidate to reach high current density and high switching frequency. So that's why I expect gallium nitride will have the explosive growth. And the silicon carbide, of course, it will be the steady growth, maybe 10% plus minus 5% every year. Okay, so gallium nitride, unfortunately, TSMC just announced they give up this business. I think this is probably too small for them to carry on. So gallium nitride still have the future, and also the silicon carbide. And because this is compound foreign, so I have to say something good for the compounds, right? But that's real. That's real. So ChatGPT again. Is it the real or the bubble? In the 1945, the California gold rush, actually the first fortune went to the shop who sold the shelves, okay? So it's the same situation now. The NVIDIA make the money, TSMC earn the money, and so Foxconn and Wistron and Delta Electronics as well. But with this heavy loaded rack like GB and also the Rubin servers, we are not selling the shelf. Instead, we are selling the excavators. So we have to make sure the gold mine should be big enough. Otherwise, it will be a bubble. Okay? So our server becomes so expensive. We sell this to the cloud service provider. We have to make sure the gold mine should be big enough. That will be the challenge. But actually, I drew this one, not using the ChatGPT. If you look at the mega trend from the 1980 to 2000, 2020, we have generally three. We have been through the three waves. First is PC and the internet, and now is AI. And this will continue growth because each wave represents a very fundamental needs. AI represents computing. Now we are talking about the quantum computing. So computing is still going on. The networking is still going on. We have the satellite, low Earth orbital. And the AI represents the intelligence. And the intelligence needs everywhere. So for myself, I'm more optimistic for the future of the AI servers. Okay, this is my conclusion. I think you can read it. But before the ending, I would like to say a few words. I'm so glad to see so many young generations show up in the audience. I started my semiconductor career in my early 20s, and it has been more than 40 years. I really appreciate Taiwan. This island provides me such a great opportunities. And in the meanwhile, I can contribute something. So now I'm in the last mile of my career. So for those young generation, you have my best wish and blessing. Keep the momentum going. This is now easy to build up this guidance mountain. Thank you for your attention.
Well, very impressive talk today. As you may know, the AI, most important, one is calculation power, like a GPU. Another is, how do you deal with high electricity consumption? One is the cutting the power consumption, another the heat dissipation, all right? So as a Delta is one of the top the system house in the world to handle the power management. In Taiwan, we have the whole ecosystem to support this kind of a technology. And as I should call you professor, okay? Since I know he was a professor. So Professor Jen said a very, I was deep thinking from his heart. We need a next generation, younger generation to continue this pattern. And, so we can carry this fire, continue to the next generation. And as you may know, in this morning session, beginning with a professor, and in the morning session, the ending will be Xiangqi. He's actually professor as a PhD student in her PhD time, all right? So we have a very good, from the younger generation to the old generation to carry the baton of this and to the next generation, okay? So let's welcome the Q&A for Dr. Jen. Please.
Yeah, I'm Hiroshi Wai from NYCU. And thank you very much, a very nice overview. I have a question about the possibility of a 48 volt to 0.7 volt direct conversion. And if you think so, what kind of technological development are requested to establish a very high efficient power conversion for 48 to directly 0.7?
Direct from 48 to 0.75 is a big challenging. And because, we need all the, because your output voltage is 0.75. So your module, because 0.75, you need lots of the current. So in this case, your module should be very close to the chips. And if your module 48 to 0.75 cannot be squeezed into this very limited space, even the vertical power division or the IVR in the CoWAS. So they will probably be used in the general, that the power density is not so high. But for the higher power density, no way you can use this power module from 48 to 0.75. That's my answer.